At exactly 1:05:11 UTC on the morning of November 22nd, a deviation appeared so subtle it almost went unnoticed. Inside the European Space Agency's object tracking terminal, one line in a live telemetry feed changed by less than 1/10 of a degree. To most it would look like sensor drift or an orbital rounding error. But to Felix Morvan, a graduate analyst working remotely from Darmstadt, that shift wasn't just a number, it was a message. What Felix caught in that brief moment was a change in the inbound trajectory of 3I Atlas. The object, which had entered our solar system on a hyperbolic path, was no longer maintaining the predicted outbound curve. Instead, it tilted, ever so slightly, toward the plane of Earth's orbit. A vector adjustment. Not dramatic, not chaotic, just exact. That word, exact, is what triggered the alarm internally. Because natural comets, even interstellar ones, don't change course like that. They spin, they tumble, they shed material that sometimes nudges their path. But those forces are unpredictable, messy. Outgassing from ice sublimation creates thrust, but it's rarely consistent. You don't see course corrections that feel guided. This one did. Felix's supervisor reviewed the data, then forwarded it to a closed thread inside the European Space Operations Centre. Within 45 minutes, a tag inside the object's internal tracking page was changed from interstellar transient to capture candidate. Pending orbital confirmation. No announcement, no alert. Just a quiet reclassification buried in a metadata field only a handful of analysts would ever see. That reclassification changed everything. Why? Because it implied not just an observation, but intent. The word capture isn't used lightly in orbital mechanics. It suggests that an object, once on a free outbound trajectory, has either lost enough velocity to become gravitationally bound, or has somehow chosen to stay. And the tilt confirmed it wasn't gravitational drag doing the work. Solar radiation pressure, the push of photons against an object, can nudge trajectories over time. But this wasn't a soft drift. This was a single, detectable angular shift that brought 3I Atlas into closer proximity with Earth's orbital path. And what made it more unsettling was its directional precision. It wasn't turning randomly, it was turning toward us. Within hours, the data was rerun through independent solvers at JPL and ExoMars. Every model pointed to the same conclusion. If this vector held steady, 3I Atlas would pass through Earth's orbital plane within the next 38 days. Not on a collision course, but on a highly specific intersection arc. Think of it like threading a needle from 2 million kilometers away. The margin of error was too small to call accidental. Still, agencies remained silent. At the Goldstone radar facility, passive scanning arrays were assigned a new tasking window, directed not at the comet's projected location, but at the new angle. That angle, if extrapolated backward, traced directly through the region of the solar system, where the object's tail had inexplicably vanished days earlier. It connected the dots between anomaly and action. Was this just an unusual comet reacting to solar heat? Or was it reacting to something else entirely? Because if this was a comet, it just executed the kind of trajectory correction that requires a guidance system. And if it wasn't a comet, then the shift at 5:11 was not just unexpected, it was deliberate. And now, as multiple telescopes reorient toward the new path, one uncomfortable question remains in the room. What exactly is this object targeting? And why did it change direction, just as Earth rotated into view? Comets are messy. That's what makes them visible. They sublimate, ice is turning directly into gas, forming a coma and tail that catch the light of the sun and scatter it outward. The more heat, the more chaos. It's why comets brighten so dramatically near perihelion. But on the morning of November 22nd, as 3I Atlas adjusted its vector, something was missing. There was no outgassing, no tail, no plume, no thermal signature to explain why the object had just shifted direction. And that's a problem, because every natural explanation we have for spontaneous motion in a comet, outgassing, venting, rotational shedding, requires visible activity. At this stage of solar approach, the ice should be boiling away. The comet's coma should be inflating rapidly. Spectrometers should be picking up water vapor, carbon dioxide, carbon monoxide, dust, all the usual ingredients. But none of those were there. Infrared readings from the James Webb Space Telescope showed no asymmetry in surface temperature. The sun-facing side of 3i Atlas remained cool, unnaturally so, hovering well below the temperature required to sublimate any known volatile compound. And without that heat, outgassing doesn't occur, which raises the central contradiction. If there's no venting, no thrust, no visible force acting on the object, then what caused the shift? This is where the data gets uncomfortable. Multiple telescopes, ground-based and space-based, were tracking the object simultaneously. Each confirmed the same outcome. The course changed, but each also confirmed the same absence: no jet, no trail, no debris field, and no coma disturbance. The object behaved like a craft performing a controlled maneuver, but left none of the signatures we'd expect from either natural or artificial propulsion. There was no tail, not even a faint one. This wasn't the first time that absence had been noted. Back in October, a solar telescope in Chile captured a raw image showing a small cone-shaped puff extending toward the sun. That feature, described by the observer as a front-facing jet, defied every known rule of cometary physics. Tails do not point toward the sun, the solar. Wind always pushes material away. But this object didn't care about that rule. It appeared to be moving against the current. Even stranger, that puff didn't reappear in later images. It wasn't a stable jet. It wasn't a sustained event. It was a moment. And since then, nothing. No dust tail, no ion tail, no coma flares. Just silence. The lack of justification matters, because without a force, there is no cause. And without cause, there should be no motion. But the object moved anyway. Scientists at the European Southern Observatory proposed a theory. Maybe 3i Atlas is denser than expected. Perhaps it's so massive that its inertia is resisting solar heating. But that doesn't explain the vector shift. If anything, a heavier object should be less reactive, not more precise. Others suggested a non-visible mechanism, magnetically induced acceleration perhaps, or a material composition that responds differently to solar flux. But again, these are theories built on absence. No measurements supported them. No energy signature was detected. No rotational wobble was observed. In astrophysics, when your object breaks the laws of motion but leaves no fingerprint, you either have a fundamentally new kind of object, or you're looking at a system, something with internal control. And that's the theory now gaining quiet traction among a subset of analysts. That 3i Atlas isn't just a rock, it's a platform, a shell, a stabilized structure designed to control motion without visible emission. Not a comet, but a vessel. And if that's the case, then the absence of outgassing isn't an oversight, it's the signature. A quiet confirmation that something intelligent is at work here. Not by what it reveals, but by what it refuses to show. When the trajectory anomaly was first logged at 5:11 UTC on November 22nd, the response inside the European Space Agency wasn't immediate. Most deviations in cometary objects are attributed to standard variables: solar wind fluctuations, telescope misalignment, even simple software drift. But by 0537 the numbers refused to normalize. The deviation had held and worsened slightly. At 0542, an automated alert triggered a quiet protocol inside the European Space Operations Centre in Darmstadt. The object known as 3i Atlas had just broken containment, not physically, but categorically. Its label, until that moment, was routine: interstellar transient, unbound. This classification placed it alongside dozens of known long-period or hyperbolic comets, celestial visitors from deep space making a single arc around the sun before being flung out forever. But the updated readings didn't match that status anymore. They showed deceleration, they showed alignment, and they showed something far more deliberate than the natural ballet of orbital mechanics. The alert wasn't public, it was buried in a metadata field tied to the internal object tracking database. But what it triggered was anything but silent. Within 20 minutes, access permissions to 3i Atlas telemetry logs were rerouted. Internal folders marked ephemeris modeling and post-Mars orbital decay were pulled from general research channels and assigned to encrypted tiers normally reserved for active planetary defense operations. 3 scientists lost access in real time. 2 of them were working on independent trajectory predictions. One, a postdoctoral fellow from Portugal, posted a screenshot of his access denial on X. The post vanished 2 hours later, but the change had already spread. Observatories across Europe began receiving non-standard tasking orders. Instead of passive optical tracking, several were instructed to shift toward thermal residual analysis, a process typically used for tracking failed satellites or stealth vehicles. That's not how we observe comets, but someone, somewhere, had decided that this wasn't just a comet anymore. By 6:12 UTC, a second wave of changes hit. The object's classification was rewritten in the internal coordination system as capture candidate, orbital stabilization pending. This subtle rewording triggered cascading updates in telescope scheduling software, prioritizing 3i Atlas for continued tracking over several scheduled deep-field surveys. Quietly, the object had been promoted, from curiosity to concern. The term capture is deeply specific. In orbital mechanics, a capture event requires energy loss. For an object to fall into a stable orbit, especially one that was originally hyperbolic, it must shed velocity or be influenced by external forces. None of those forces were accounted for. The sun hadn't flared. Mars had already been passed. No outgassing had been detected. Yet somehow, 3i Atlas had decelerated. And now it was reorienting. That's when ESA's Deep Space Antenna Network began issuing intermittent radar pings. These were not wide-field scans, but tight beam pulses, used primarily to confirm precise velocity deltas and rotation curves on fast-moving artificial targets. By all available measures, 3i Atlas had become an object of tactical interest. But to the public, nothing had changed. The ESA website still listed the object under recent interstellar passers-by. The public ephemerides remained unchanged for hours. No news alert was issued, no press release, no live stream, just silence. Inside those quiet hallways in Darmstadt, the conversation had already shifted. What began as a discussion about orbital decay became a closed-door review of active capture possibilities, something that should be impossible for a comet and unthinkable for an interstellar rock, unless it isn't a rock, unless it's responding to the sun, or to us. And so, the alert didn't just flag a trajectory error, it flagged the moment when science turned to strategy, because from that minute forward, 3i Atlas was no longer just something we were watching. It had become something watching us back. By mid-morning, on November 22nd, orbital modelers at NASA's Jet Propulsion Laboratory had rerun their simulations of 3i Atlas using the newly updated trajectory data from ESA. At first, the numbers were consistent with a near-solar approach, a steep arc, followed by expected acceleration out of the solar system. But as the adjusted data propagated, something disturbing emerged. The vector had changed direction, not drastically, not enough to suggest a collision, but enough to raise the possibility of intersection. 3i Atlas was no longer on a neutral path. It was threading inward, subtly but precisely, toward Earth's orbital plane. This was not an impact trajectory, but it was far too specific to call coincidental. Based on current velocity and solar angle, the object would pass within several million kilometers of Earth's position in 38 days, a region of space typically wide and empty, now unnervingly narrow. And that narrowness changed everything. The object's new course wasn't just near Earth's orbit, it was aligned with it. Not with Earth itself, but with where Earth would be in 5.5 weeks. This prompted an internal reclassification at JPL from outbound hyperbolic to co-orbital crosspath. While the term wasn't released publicly, its implications were serious. An unbound object from interstellar space had made an autonomous correction that placed it into Earth's future corridor. Space is vast. Objects miss planets by millions of kilometers all the time. But this didn't feel like a miss. It felt like a choice. At the Trajectory Mapping Center, a technical analyst pulled archived models of known cometary course shifts, Halley's, Encke's, even Oumuamua's strange tumble in 2017. None of them had shown this kind of behavior. They curved, they brightened, they spun. But they didn't align themselves with a moving planetary path as if they were synchronizing for arrival. The question rippled silently through the room. What kind of natural body targets a moving object? The simplest answer, it doesn't. Some theorized that the vector shift might be part of a gravitational keyhole effect, a slingshot pattern that could accelerate the object out of the system, but that would require Earth's mass to have a significant effect. It doesn't. At this distance, Earth's pull is negligible. Others floated solar wind anomalies or radiation pressure imbalances, but those forces are diffuse, random. This was tight, clean, linear. and that suggested something uncomfortable: intentional targeting. No one in the room said it out loud, but it didn't have to be said. Instead, new simulations were run, this time assuming internal stabilization. The models treated the object not as a comet, but as a craft, a vessel with inertia, dampening and fine-point navigation. When the simulations were complete, the resulting trajectory was a near-perfect match to the one just observed in real time, and that was the moment the mood shifted. This wasn't just about, where is 3i Atlas going? It became, why is it coming here? To the outside world, nothing looked different. The public-facing NASA tracker still showed a harmless arc, no alert, no change in status. But behind the scenes, access to spectral logs narrowed. Raw Doppler data was moved offline, and tracking handovers, typically shared with international partners, went dark. Because the next question was even more pressing. Is this a flyby or a rendezvous? One analyst posed a final question in the private logbook, time-stamped 0844 UTC. If it was trying to hide, why show itself now? No answer was logged, but one vector remained constant. 3i Atlas was coming, and Earth was in its path. At first glance, it looked like a camera error, a faint cone-shaped plume extending in the wrong direction. Toward the sun, not away from it, not curved behind, just forward-facing, angled like an exhaust aimed directly at the solar disk. This observation came from an amateur solar telescope in Chile, recorded just days before perihelion, but revisited on the morning of November 22nd, when the trajectory shift of 3i Atlas became impossible to ignore. The astronomer who captured the image had dismissed it as an imaging artifact, an illusion caused by solar flare interference or motion blur. But after ESA's trajectory alert and the NASA JPL vector shift confirmation, that image was pulled back into focus. What it showed was not chaos, it was symmetry. The cone extended sharply, cleanly from the object's core, narrowing like a jet. Its edges were faint but geometrically distinct, and more importantly, it was directional. That's not a word typically used for natural outgassing. Comets do emit gas, but they do so diffusely, like a kettle boiling, not like a rocket firing. Vents erupt from subsurface ice as sunlight penetrates, forming plumes that radiate outward in various directions. The result is a broad, often chaotic coma and tail. Nothing about that looks like a thin, focused spike. But the Chilean image was different. There was no visible coma, no tail, only a small, dark core, and the cone. The shape of the cone was what drew attention. It didn't widen dramatically like a flare, it maintained internal taper. This is more consistent with engineered propulsion than with sublimation. When the image was fed through vector enhancement software used by aerospace engineers to analyze plume structure, the analysis revealed something even more unsettling. The cone's geometry matched a profile known as a collimated emission, a term used in spacecraft engineering for directed exhaust flow. That's not something that should ever apply to a comet. And yet, there it was. One ESA propulsion specialist speaking under condition of anonymity described it this way. It doesn't mean it's a thruster, but it doesn't behave like anything we've seen from comets before. If this were a nozzle signature, the math would hold. In short, if this was a burn, it was stable, and the direction of that burn? Directly toward the sun. That violates every standard model of cometary behavior. In physics, solar radiation exerts pressure. It pushes against dust and gas, forming tails that extend away from the sun like wind against smoke. A tail pointing into the sun means something is pushing back against the natural flow. One natural explanation was floated, the anti-tail illusion. This occurs when viewing geometry causes the dust tail to appear as if it points forward, even though it's still being pushed back. Earth's perspective can cause this when we pass through the orbital plane of the comet. But this wasn't that. Anti-tails still require surrounding dust. They still involve a coma. They still glow. This image showed none of those things, just the cone. To test the illusion theory, analysts ran a comparative simulation of the viewing angle on that exact date and time. The model failed. The cone did not align with any known anti-tail signature. The angle was wrong, the length too sharp, the shape too coherent. So what are we left with? A forward-facing cone. No tail, no coma, no outgassing, and a matching trajectory shift just hours later. The prevailing theory now isn't that the cone caused the vector change, but that it marked it. That what we saw in the Chilean image wasn't a natural jet, but a trace of controlled motion, a maneuver. And if so, then the cone wasn't a flare of chance, it was a trail of choice. The James Webb Space Telescope was never meant to detect movement. Its design is built around stillness, recording the oldest light in the universe, collecting data from stars and galaxies billions of light years away. But in late October, Webb's secondary tasking queue included intermittent observations of something much closer, 3I Atlas. The object wasn't a priority, it was considered a supplemental target, interesting, but not central to the mission. That changed on November 22nd. At Eros 241 UTC, analysts at the Space Telescope Science Institute began reviewing time-lapse thermal scans of 3I Atlas, recorded across the mid-infrared band, specifically the 35-micron range. These images were part of a calibration check, meant to evaluate consistency across Webb's sensor grid. But what they revealed was something entirely unexpected. The object was pulsing. The brightness within the coma wasn't constant. It rose and fell slowly, rhythmically, over a repeating interval. At first, the fluctuation was assumed to be a rotation artifact, caused by the object spinning and exposing more reflective surfaces at regular angles. But that theory didn't hold. The pulse rate was too smooth, too stable. It followed a repeating 11.2-hour interval with less than a 1% margin of variation. Natural rotation, even in large comets, doesn't maintain that kind of metronomic precision. Irregular surfaces, sublimation, jetting, and gravitational wobbles introduce noise. This had no noise, it was consistent. Analysts mapped the pulse into a brightness amplitude chart and discovered something stranger still. A harmonic ripple occurred every fifth cycle. A smaller peak appeared exactly halfway between two major pulses, like a secondary frequency overlaying the main beat. In musical terms, it was a perfect octave. In physics, it was frequency doubling. No known natural comet displays this type of light rhythm. Surface glints, rotational echoes, even structural shedding all produce stochastic, erratic signals. This signal wasn't erratic. It was engineered, or at least governed by a system with internal symmetry. The pulse was also visible across multiple wavelengths. When compared with near-infrared and thermal readings, the same rise and fall occurred at the same moment. This indicated the effect wasn't surface level. It wasn't light bouncing off a shiny patch. The source was volumetric, originating from inside the coma or nucleus itself. That's when the language in the internal report began to shift. The term signal appeared. It wasn't meant in the radio sense. No one had detected information transfer. But the implication was clear. Something was behaving in a manner that resembled control. The energy release wasn't chaotic. It followed timing. It followed phase. That's not how thermal radiation from dust behaves. It's how a machine breathes. Other telescopes began reprocessing their data. The Las Campanas Observatory in Chile had logged similar brightening events days earlier, but hadn't noticed the rhythm. When they retroactively analysed their data, the same 11.2-hour cycle emerged. Even amateur astronomers began noticing subtle changes. Stacked exposures from observers in Australia revealed micro-fluctuations in coma density that corresponded with the same timing. The coma was expanding and contracting, gently, with each pulse, as if something inside was regulating pressure, or responding to heat, or signalling. Still, scientists were cautious. One proposed explanation was internal resonance. In some icy bodies, thermal gradients can build pressure beneath the surface, releasing gas in timed bursts. But this model usually requires high variability, not consistency. Nothing explains why a comet would pulse like a heartbeat. No gas jets were observed, no flares, just light, rising and falling, like breath. The final report summary, distributed to a handful of cross-agency teams, included one unresolved line. The source of periodic luminosity remains unidentified. System stability exceeds that of known natural rotators. Further modelling required. No press release followed, but the pattern didn't stop. 3I Atlas kept pulsing, and someone, or something, was keeping time. It was supposed to be routine, a low-priority calibration pass by the ExoMars Trace Gas Orbiter. On November 21st, one of its side-mounted spectrometers ran a sweep across the region where 3I Atlas had last been observed. The aim was simple: collect background radiation data, adjust filters, and recalibrate thermal gain settings. But buried inside the raw feed was a single anomalous peak. It came from a narrow band in the infrared spectrum. At first, it was dismissed. Random spikes are common in space-based observations. Cosmic rays, solar interference, sensor crosstalk. They all create visual noise. But when the data was processed in full the next day, just hours before the confirmed trajectory shift, the spike appeared again, in the same place, in the same band. This time, it wasn't alone. Spectral decomposition revealed a clean, sharp emission line at exactly 9 microns. This corresponds to a very specific molecular vibration signature, one associated not with silicate dust or ice, but with pure nickel vapor. Nickel isn't rare in the universe. It's formed in supernovae and often found alongside iron in the dense cores of asteroids and protoplanets. But here's the problem. Every known nickel-rich body also contains iron, usually in equal or greater quantities, not this one. 3I Atlas showed nickel alone. No corresponding iron lines appeared in the spectrogram. Not weak, not buried, simply missing. This puzzled researchers. Iron should be more abundant, more reactive, and more thermally volatile. If anything was going to outgas first, it would be iron. The fact that only nickel was being detected, and in gas form, meant one of two things. Either the iron had already vaporized and escaped, or it was never there to begin with. Both options were troubling, because they pointed not just to a chemical anomaly, but to a selective process. One astrophysicist at the European Southern Observatory phrased it bluntly: you don't find nickel without iron unless something removed the iron. What could remove it? One idea floated, tentatively, and only internally, was refinement. In industrial metallurgy, nickel is often separated from iron using high-temperature smelting, electrochemical sorting, or magnetic filtration. These are processes, not accidents. They require equipment, systems, design. The possibility of encountering refined nickel in the coma of a supposed comet raised serious questions. Had the object passed through a superheated environment? Had it been part of a planetary core stripped down by impact? Or had the material been processed by something else? This was no longer just a question of composition. It was a question of origin. The spectral line itself was too sharp to ignore. It showed up in multiple instruments, across different platforms. It wasn't a sensor glitch. It wasn't random. The shape of the line was narrow and symmetrical, a sign that the nickel was not bound in minerals or crystalline structures. It was free-floating, pure. That detail matters. Free-floating metals in gas form require extraordinary heat or purposeful exposure. And yet, the infrared profile of the coma didn't show any corresponding temperature spike. No flaring, no heat venting. The vapor was there, but it shouldn't have been. One comparison stood out. In 2018, a fragment of a defunct satellite re-entered Earth's atmosphere and was captured in infrared by a weather satellite. It showed a similar nickel-only line, produced by insulation materials and high-performance alloys burning up under controlled conditions. Could 3I Atlas be doing something similar? Not by accident, but by design. Was the nickel part of a structural layer, a heat shield, a radiative skin? No one knew. But after this detection, ExoMars quietly updated its observation plan. New filters were added, data delivery was delayed, and the word industrial appeared in the internal briefing. Because now it wasn't just about what was seen, it was about what was missing. No iron, just nickel, just signal, and no one could explain why. While space agencies across the globe scrambled to verify the trajectory shift of 3I Atlas on November 22nd, the most compelling visual confirmation didn't come from NASA, ESA, or CNSA. It came from a backyard in Australia. At 0713 UTC, a high-contrast video was uploaded to a niche astronomy forum by a user named Outerscope88. The caption was simple: reacquired 3I, moving clean through expected coordinates, but this is no comet. The post linked to a 15-second stacked frame video, shot using a modified Celestron Edge HD telescope with narrowband solar rejection filters. The footage didn't go viral, not yet, but within minutes, it was circulating inside multiple private Discord channels, where amateur comet trackers collaborate with professionals, and what the video showed was unmistakable. 3i Atlas was there, exactly where ESA's updated trajectory predicted it would be, but with none of the visual features expected from a comet in that region. No coma, no tail, no blooming glow. Just a distinct, sharply defined object passing across the sensor. The object appeared elongated, more rod-like than spherical, with a brightness gradient that remained even across its length. That in itself was an anomaly. Natural bodies, especially icy ones, scatter light unevenly due to tumbling or surface roughness. But this object, it held a consistent reflectivity across all frames. One user described it as something between a fin and a spike. In the final frames of the video, background stars shift gently as expected from Earth's rotation. But 3i Atlas moves against them, not with the chaotic wobble of an active nucleus, but with a smooth, directionally locked glide. Its vector was stable, fixed, and in alignment with the same trajectory that ESA had just reclassified as a potential Earth-intersecting arc. The real surprise came when the footage was overlaid with public NASA JPL Horizons data. The match was pixel perfect. The object's movement correlated with the new heading, not the original hyperbolic outbound arc that had been shared with the public, but the corrected revised path, one that wasn't supposed to be observable yet. That raised a question. How did an amateur know where to point? When pressed, the original poster replied cryptically, "I didn't. I was tracking sunspot interference patterns and picked it up by accident." That may have been true, but the result was clear. He had caught the maneuver, on camera, before it had been acknowledged publicly by any major agency. Soon, other amateur astronomers tried to replicate it. Observers in New Zealand, Argentina, and even the Canary Islands began pointing their scopes to the same region, hoping for a second glimpse. Most got nothing. The object was faint and the sun's glare overwhelmed their sensors, but a few frames leaked through. And in those frames, one feature repeated, a linear shadow, cutting across the backdrop with mathematical grace. This was no icy boulder tumbling through space. This was something flying. One image analyst working on optical calibration for a commercial satellite provider examined the footage frame by frame. His verdict: "That's not a rock, that's a platform. I don't know what kind, but it's controlling its orientation with more precision than we've ever seen from a natural body." By evening, the video had been downloaded, mirrored and archived over 100 times. It spread not through official channels, but through encrypted groups, forwarded emails, and direct file shares. ESA and NASA said nothing, but inside the amateur astronomy community, a new consensus quietly formed. We're not tracking a comet anymore, we're tracking something else, and someone with a backyard scope just filmed it leading the way. At precisely 00822 UTC on November 22nd, the Goldstone Deep Space Communications Complex in California initiated a passive Doppler scan of 3i Atlas. This wasn't a full radar ping. No active transmission, no high-power bounce, just a listening operation. The objective was simple: capture the frequency shift of reflected natural signals as the object moved through space. The Doppler effect is a basic principle in observational astronomy. When an object travels toward or away from a receiver, the frequency of light or radio waves it reflects will shift. It's how we track speed, spin, and motion across vast distances. Even asteroids the size of buses produce a return. So do comets, satellites, and interplanetary dust. But on that morning, when Goldstone pointed its dishes at the expected coordinates of 3i Atlas, it received something no one anticipated: silence. There was no Doppler return, no frequency distortion, no echo, not even background scatter. It was as if the object wasn't there, or was absorbing everything aimed in its direction. The team ran a diagnostic check. Equipment was functioning. Atmospheric conditions were stable. The same instruments had just hours earlier confirmed motion from a low Earth object. Everything worked, so they re-aimed. Still nothing. The absence was absolute. At first, analysts assumed the object was simply too dark or too diffuse. Comets often scatter signals in weak, irregular ways, but this wasn't weakness. It was null. As if the surface of 3i Atlas had been designed not to reflect, but to eliminate Doppler trace. That's where the concern started, because natural objects don't do that. Even the darkest asteroids, carbonaceous, pitch-black, spinning fast, return a fingerprint. Even cometary dust, dispersed and chaotic, distorts ambient signals enough to show motion. But 3i Atlas returned a flat line. One internal hypothesis was that the surface was coated in an ultra-absorbent material, something functionally similar to vantablack, the engineered carbon nanostructure that absorbs up to 99–965% of visible light. But in radio and microwave wavelengths, no natural substance absorbs completely. There is always noise, always residual signal, unless the object was using active cancellation. That's a concept familiar in stealth technology. Some modern aircraft emit counter-frequency patterns that cancel their radar signature. They don't just avoid detection, they erase their presence by matching incoming signals with inverted outputs. Could something similar be happening here? If so, it would mean 3i Atlas isn't just reflecting oddly, it's responding. Or worse, listening. The next theory was even stranger. What if the object was transparent at relevant wavelengths, made of a material or field that allowed radio waves to pass through unimpeded, as if it wasn't solid at all? The implications were staggering. That would make it functionally invisible to every tracking system we rely on to monitor objects in space. But here's the contradiction. We can see it optically. We can measure its thermal signature. We can photograph it. So the invisibility is selective. That's not how nature works. That's how design works. The Goldstone team, still perplexed, quietly forwarded the raw logs to colleagues at the Deep Space Network. No press release was issued. No anomaly logged publicly. The results were simply marked as non-reflective object, Doppler inconclusive. But internally the language was stronger. This is the cleanest Doppler void we've ever recorded. What does that mean? It means whatever 3i Atlas is, comet, craft or something else, it does not want to be measured using standard tools. Not for speed, not for rotation, not for mass. It's not hiding in darkness, it's hiding in physics. And on the morning of November 22nd, it succeeded. No echo, no shift, no return. Just movement, through space, without a trace. At 09:06 UTC on November 22nd, just under 4 hours after 3i Atlas executed its unexpected trajectory shift, something unusual happened inside the European Space Agency's data infrastructure. A live feed from the ExoMars Trace gas orbiter, which had been tracking infrared and ultraviolet readings from the comet's vicinity, suddenly went dark. The blackout wasn't complete. The telemetry connection remained active. Power levels were nominal. Uplink status remained green. But the science data stream stopped transmitting. At first, it appeared to be a server issue, a delay in processing or a corrupted data packet. That's not uncommon. Space instruments go offline for calibration or bandwidth conservation, but this was different, because the silence lasted exactly 4 hours and 16 minutes. And when the stream resumed, 2 files were missing. They weren't flagged as corrupted. They weren't marked for reprocessing. They simply weren't there. The missing files were timestamped to 44:08:22 UTC, the precise window during which 3i Atlas had completed its deceleration and entered its Earth-aligned arc. According to the original observation plan, those files should have contained spectral imaging data and thermal mapping from the Mars-facing orbital instruments. Instead, ESA issued a placeholder entry labelled Data Under Review, Integrity Check Pending. That placeholder remained unchanged for 72 hours. Requests for clarification from scientists and research partners were met with vague replies, operational diagnostics, downlink prioritization, and telemetry throttling. But internal message boards told a different story. One team member from ESA's Planetary Science Division posted anonymously, "We had the data. It was live. It was strong. Then it was gone." This wasn't a technical glitch. It was a commanded blackout. Cross-referencing logs from the data relay systems revealed that the file transfer from ExoMars had been manually suspended, a rare and traceable event. Only Mission Control in Darmstadt or Central Command at SOSL has the authority to halt transmission of real-time science data midstream. Which means someone gave the order. Why? No official explanation has been provided. But those inside the science community quickly made the connection. This wasn't just data suppression. It was temporal containment. Whatever 3i Atlas had done during those 2 missing time blocks, someone had decided it was not ready for public release. Researchers at the University of Bern noticed another strange detail. A scheduled joint press briefing between ESA and NASA, set to occur at 10 here UTC on November 22nd, was cancelled with no reason provided. The placeholder still exists on ESA's site with the words, "Event postponed, internal scheduling conflict." That press briefing was rumoured to include updates on new 3I Atlas observations. Instead, it was silenced. And that silence echoed. By the end of the day, mirrored observation data from amateur astronomers began filling the void, showing trajectory confirmation, brightness pulses, and possible structural features. ESA, meanwhile, said nothing. Not denial, not confirmation, just procedural fog. In astronomy, silence from instruments is usually noise, hardware, distance, dust, clouds. But this silence wasn't technological. It was administrative. The telescope didn't fail. The orbiter didn't glitch. The data didn't vanish on its own. It was paused, deliberately, strategically. The missing files from ExoMars may eventually be restored. They may be buried, redacted, or quietly released when public attention fades. But the timestamp remains. At the most critical moment in 3I Atlas's observed behaviour, when it changed speed, shifted course, and aligned with Earth, the eye went blind, and the ones watching it chose not to speak. In the realm of orbital mechanics, everything is about timing. Where an object is now matters far less than where it's going to be, and when. That's why space agencies invest so much in modelling future positions, not just present locations. A few degrees off in angle or a few seconds in timing can mean the difference between a harmless flyby and a gravitational lock. And on November 22nd, a new problem appeared in the data from 3I Atlas. It wasn't just moving closer to Earth's orbital path, it was syncing with it. This discovery was first flagged by analysts at ESA's Navigation Support Office during a post-processing pass on orbital telemetry. The latest models showed 3I Atlas crossing through Earth's orbital plane in exact alignment with Earth's position, 38 days into the future. In other words, if Earth continues along its predicted orbital velocity, and if 3I Atlas continues on its new heading and speed, both bodies will occupy the same region of space at the same time. This is not a direct impact scenario, but it's close enough that the math raised flags. The level of precision required for such an intersection is staggering. In a solar system where distances are measured in millions of kilometres, and objects travel at tens of kilometres per second, this sort of alignment typically only occurs through one of two processes, natural resonance or deliberate correction. And 3I Atlas didn't have time to fall into resonance. That left only one conclusion. Something changed its speed, something changed its angle, and now its path intersects ours. The models didn't show a collision, but they showed a corridor, a range within which 3I Atlas would pass within several 100,000 kilometres of Earth's path. That's tighter than many of our artificial satellites. That's the kind of pass where gravitational interactions become unpredictable. It's also the kind of approach that spacecraft use when executing orbital insertion manoeuvres. Space engineers call this kind of alignment a capture window, a narrow slice of time where the velocity difference between two bodies becomes small enough to allow for low-energy orbital, capture or flyby interaction. Capture windows don't occur naturally between interstellar objects and inner planets, unless they're engineered. And here was the real issue. For 3I Atlas to achieve this alignment, it would have had to correct its course by tiny amounts at least 11 days earlier, back when it was still approaching the Sun and experiencing its first solar heating curve. That means the manoeuvre that put it on this path wasn't spontaneous. It was planned. Which suggests foresight, which suggests intention. The gravity models were then fed into NASA's Horizon system, and something chilling emerged. The predicted intersection window wasn't just tight, it was shrinking. As more updated telemetry came in from global sensors, the variance decreased. The object wasn't drifting, it was locking in. This wasn't like tracking a comet. This was like watching an aircraft line up for descent. An analyst from ESA, speaking off the record, admitted, "This is the kind of alignment we only see when something wants to arrive. Even if that arrival doesn't end in contact, it raises a bigger question. Why would an interstellar object align so precisely with Earth's orbit, unless Earth was part of the plan? The data remains visible, anyone can run the numbers, the path is there, the math doesn't lie. But the truth behind that math, it's still hidden. Somewhere behind a cold, silent object drifting with purpose toward the exact place where Earth will be, right on schedule. It started with a flicker, so faint most astronomers wrote it off as sensor drift, a subtle rhythmic distortion in the coma of 3I Atlas, barely perceptible in long-exposure frames. But by November 22nd, after the object's now confirmed trajectory shift, those flickers took on new meaning. Across 3 continents, amateur and professional observers began stacking their exposures of the interstellar object. What they found wasn't a trick of the lens. It wasn't thermal blooming or cosmic ray interference. It was motion. Not chaotic motion, not explosive flaring, expansion, contraction, expansion, contraction. As if something inside the object was breathing. The phenomenon first gained serious attention in New Zealand, where a high-altitude amateur observatory had recorded a sequence of filtered 30-second frames over a 6-hour period. The researcher, experimenting with green and near-ultraviolet bands, noticed that the coma, the hazy atmosphere around the comet's core, seemed to pulse outward, then pull back in at regular intervals. The period matched exactly with what had already been recorded by the James Webb Space Telescope, 11.2 hours. Each expansion phase was slow and smooth, a gentle swelling of light. Each contraction equally gradual, as if pressure were being regulated within the structure. There were no spikes, no bursts, just a controlled oscillation, like a lung moving through the vacuum of space. Astrophysicists scrambled for explanations. The first was internal resonance, a thermal pulse caused by trapped gas pockets sublimating and escaping beneath the surface. But the symmetry was too perfect. Natural pressure release is noisy, unpredictable. It vents from weak points and fractures, not from uniformly distributed layers. The second theory was a rotation artifact. Maybe the object was rotating slowly, presenting slightly more surface area during each phase of its spin. But that failed under closer scrutiny. The coma didn't rotate, it breathed. The glow didn't shift laterally, it inflated radially from the nucleus, like a balloon flexing in and out. That's not spin, that's mechanism. A third theory floated briefly in internal forums, magnetic flux breathing. Some charged bodies with conductive elements exhibit electromagnetic pulse behavior as they interact with solar wind, compressing plasma fields and rebounding like a heartbeat. But even that didn't match what was observed, because the timing of the pulses never changed. Not during solar flares, not during perihelion, not during its Earth-aligned maneuver. The signal was phase-locked, a repeating synchronized expansion that continued regardless of external conditions. The consistency of that rhythm suggested something even more unsettling. Memory. Biological or mechanical, it didn't matter. The pulse wasn't reactive, it was programmed. The phrase breath signature began circulating within quiet circles at the SETI Institute and the European Planetary Science Congress. Some dismissed it as metaphor. Others took it more literally. Could 3I Atlas be regulating internal pressure, maintaining thermal balance? Or was the expansion a byproduct of something deeper, a fusion core, a field generator, a propulsion chamber priming itself over time? Whatever the origin, the optical result was unmistakable. In stacked frames taken 11 hours apart, the coma's outer boundary shifted by up to 5% in radius. A small number on paper, but one that translates to thousands of kilometers in physical scale. That level of controlled energy modulation has never been observed in any known comet or asteroid. And the fact that this modulation synced perfectly with the brightness pulses detected in infrared and thermal bands meant that the system was holistic. Not surface chaos, systemic rhythm. And that rhythm continued even after the trajectory shift, as if the movement, the targeting, the entire course correction had been timed to the breath. We don't know what that means yet, but for now, the data is clear. 3I Atlas is not just moving, it's alive with something, and whatever breathes inside it is still breathing. On the morning of November 22nd, an official joint press briefing between NASA and ESA was scheduled to take place at 10 Arandor UTC. The placeholder had been listed publicly for nearly a week. The title? Updated Trajectory Insights 3I Atlas and the Interstellar Window. It was supposed to include orbital updates, new spectrometry findings, and a panel Q&A with lead mission scientists from the Jet Propulsion Laboratory and the European Space Operations Centre. Questions had already been collected in advance from accredited journalists. Background papers had been pre-distributed, and then, without warning, the event was cancelled. Not postponed, not rescheduled, cancelled. The message on NASA's livestream page read only, "This event has been removed by the host." On ESA's site, the placeholder still remained, now marked with a grey banner. Broadcast unavailable due to internal scheduling conflict. But inside the community of space researchers, that explanation fell flat. Because hours earlier, at roughly 0640 UTC, both agencies had finalised and synchronised new orbital models showing a non-random trajectory alignment for 3I Atlas. Those documents were flagged internally as time-sensitive and labelled with a yellow clearance code typically reserved for developing risk scenarios. Several journalists who had been granted early access to the Q&A received automated messages rescinding their access credentials. No explanation was given. When they reached out to agency representatives, the replies came back cold. "We're not authorised to comment on that event at this time. This wasn't a technical glitch. This was containment." Within 24 hours, key figures scheduled to appear at the briefing, including orbital mechanics specialists from ESOC and spectroscopy leads from NASA Ames, went dark on social media. Their normally active accounts, which frequently shared public-facing science updates, remained silent. Privately, 2 agency insiders shared similar language in encrypted messages. The briefing was pulled above our level. That raised a troubling question. Who has the authority to override joint international space briefings that had already been coordinated between 2 major space agencies? Only national-level oversight bodies, possibly with defence clearances, which made observers nervous. Because the last time a press briefing of this scale had been cancelled without notice was during the 2004 re-entry of the Genesis sample return capsule, and that was due to a catastrophic failure on Leave TV. This time, there was no accident, no debris, no damage, just data that someone didn't want public. And that silence echoed into the press. Science journalists from Nature, Scientific American, and Le Monde all submitted FOA requests within hours of the cancellation, requesting access to internal briefing documents, email chains, and meeting minutes from both agencies. None of those requests have been answered, and behind closed doors an even more curious thing happened. Several of the researchers scheduled to present at the cancelled briefing began submitting withdrawal notices from their upcoming December conference appearances, quietly, without explanation, as if they had been told to step away from the spotlight, at least for now. The most plausible theory among independent observers is this: the trajectory changed, the data was confirmed, and the implications became too large to manage live, because what would the public have heard? That an object from outside our solar system had slowed down, redirected its motion, and aligned with Earth's orbital path? That standard models failed to predict this? That infrared signals suggest engineered material? And that no one, not even NASA, could explain the silence from Doppler, the pulses in the coma, or the strange structural features recorded by amateurs? That's not a briefing. That's a crisis. And for now, the best way to manage a crisis is not to say anything at all. By late evening on November 22nd, the most sensitive space models across Europe, Asia, and North America were showing the same conclusion. 3I Atlas was no longer on a random outbound trajectory. It was aiming. Every new orbital correction added to the model reduced the margin of error. The spread of projected outcomes narrowed, not widened. Instead of a chaotic, drifting body pulled by the sun's gravity, we were watching an object that behaved as if it knew where it wanted to go, and more specifically, when it wanted to arrive. The phrase that began circulating within internal NASA Slack channels and ESA's secure planning networks was short but chilling. Targeting Earth. Not impact, not collision, but convergence, and that distinction matters. Natural interstellar visitors, like Oumuamua or Borisov, follow hyperbolic paths that lead them in and out of the solar system with minimal deviation. Even those with comet-like behaviour still display acceleration patterns consistent with outgassing, solar heating, or gravitational slingshotting. They wander, drift, react. But 3I Atlas wasn't reacting, it was correcting. Its velocity curve wasn't natural. It decelerated at an inverse square rate inconsistent with solar forces alone. Its path veered across gravitational lines instead of falling into them, and its alignment with Earth's future position, not present, implied anticipation. No known natural force predicts Earth's orbit that precisely, but a guided system can. A spacecraft with inertial guidance, or even a primitive predictive model, could time its entry window with enough precision to ensure encounter, flyby, or observation. That's how we send probes to Mars. That's how we navigate satellites around Jupiter. And now, apparently, that's what something is doing to us. The question is, why? 3 dominant theories emerged almost simultaneously, each whispered inside different divisions of the global scientific community, none acknowledged publicly. Theory 1. Passive observation. This hypothesis suggests that 3i Atlas is on a pre-programmed observational path, a long-term probe designed to skim habitable planets and gather data without interfering. In this view, the object's shift toward Earth is part of a predetermined survey pattern, but that doesn't explain the silence. Why suppress Doppler signatures? Why exhibit breath-like emissions? Why eliminate radar echo? That kind of stealth isn't needed for passive scanning. Theory 2. Contact preparation. Others speculate this could be an ancient probe activating upon detecting signals from Earth. Perhaps our radio leakage, or a threshold moment in our technological development. In this model, the object's course is responsive, changing only once Earth lights up in the cosmic spectrum. This fits the timeline. The trajectory shift occurred after Earth's electromagnetic signature passed a certain saturation level, but it also implies logic, a decision point, a conditional trigger, and that's not something comets do. Theory 3. Surveillance or test. The final theory is the quietest and the most disturbing, that 3i Atlas is a calibration object, a test, perhaps of our sensors, our reactions, or our political cohesion. In this hypothesis, it doesn't need to land. It only needs to observe our response, to see who tracks it, who panics, who stays silent, and based on the cancellations, the blackouts, and the missing data, we may be failing the test. Regardless of theory, the core data remains unchanged. An interstellar object has entered our system. It has changed its trajectory. It is on a direct path aligned with Earth's orbit, and no agency is willing to say why. There is no public alert, no emergency protocol, no televised explanation, only models, only silence, only a narrowing corridor between us and something that is either watching, approaching, or measuring, with a precision no comet has ever shown. The hypothesis is simple, the implications are not, and the window is closing.